Okay, looks like the stream is live. So how's everybody doing this morning? Huh? Mashkajich? Yeah. Mashkajich. There we go. Yeah. Cole's practicing his Klingon pronunciation. It's getting better. So, okay, so let me go over to, let's see. That is not what I wanted. I need to make a new scene. And we'll do window capture. And we'll capture preview. Okay. And then we'll fit the screen. Okay, great. Okay, so those of you who are online, if you go to Canvas and go into the Files section, there's some folders. One of them is called In-Class Worksheets. Within that, there's a folder for each chapter. So the file that we're looking at here is 5.5. So it's in Files, In-Class Worksheets, Chapter 5, and then it's the only thing in that folder at the moment. So pull up, if you want to pull up that file, this is how you get to it. I went ahead and printed them today for those of you who are in the room because one of the things we want to do is kind of draw some stuff. So let's go back to when you guys were in Calc 1. You probably did at least a little bit of numerical integration, or even if you didn't necessarily consider it for the numeric number crunching stuff, you did for defining what an integral was, right? So a definite integral, the idea, right, was that we inscribe a bunch of little rectangles that if we add up all those rectangles, that gives us an approximation of the area. If we let the width of the rectangles go to 0, or equivalently the number of rectangles go to infinity, then this thing should be precise. And so the definite integral became the limit of a sum, in the same way that the definition of the derivative was the limit of the difference quotient or whatever, right? Okay, so but what about if we want to do an integral that basically is impossible? Or we want to do one, but it's just really impractical to try and find an antiderivative. We don't care. So here's a good example of an integral that you cannot do. Integral from 0 to 1 of e to the minus x squared dx. Okay, so how would we try to do an integral if we could? We'd want to find an antiderivative, and then once we've got that, plug in the top number, plug in the bottom number, and subtract, right? That's the whole point of the fundamental theorem of calculus. Oui ou non? Okay, so the hard part in integrating is finding the antiderivatives, right? We've got a lot of techniques for doing that, but, and this part might kind of blow your mind, there is no antiderivative of this function, e to the minus x squared. Okay, so that may seem a little bit funny. How can there not be an antiderivative of it? So let me kind of wax poetic for a minute as to what I mean by that. Okay, so there is a class of functions that we call elementary. And it doesn't mean they're really easy. It just means that, we're going to build everything out of them. So what are elementary functions? Polynomials, radicals, anything you can build out of those. So fractions of polynomials, all 6 trig functions, all 6 inverse trig functions, e to the x, the hyperbolic trig functions, let's see what else, right? Basically every basic function that you guys know, e to the x, sine, square root of x, anything like that, those are all elementary. Okay, good. So what happens if you start putting together elementary functions, right? If I say, oh, well, e to the x is elementary and sine x is elementary, can I put those two together in lots of different ways? Sure, I could add them, I could subtract them, I could multiply them, I could divide them, I could compose them. right? So there's a lot of stuff that I could do to take two elementary functions and make some new thing out of them. Is that new thing itself elementary? Well, that's a good question, right? The answer is yes, it is. Okay, so anything that you can do algebraically with two or more um, elementary functions produces an elementary function. Okay, so is that cool? Just this concept of elementary. All right, so then let's see, how does calculus enter into the mix? If you take a derivative of an elementary function, do you get an elementary function? What do you think? Okay, how do I know that that's going to be the case? Well, what are the rules for taking derivatives? There's basically three of them that we need to really think about: the chain rule, the product rule, and the quotient rule. Okay, so think about how all those things look, right? Let's take, for example, the product rule. You do one thing times the derivative of the other, and so on, right? Well, let's say you might have to use the rules multiple times, okay? But if you can follow directions and you have as much paper as you could possibly desire, no matter how massive of a function I give you, with enough time, you could sit through and crunch all of those rules and eventually get the derivative, okay? So the derivative of an elementary function is itself an elementary function, okay? Is that cool? It unfortunately does not work the other way. So there are elementary functions who are not the derivative of any other elementary function. So if you think about it sort of like you've got this big pile of elementary functions, you take the derivative of any of them and you land back in the pile of elementary functions. But if you ask yourself, here is an arbitrary elementary function, what elementary function is it the derivative of? That thing may not be in the pile, okay? And this integral is an example of such. Okay, so e to the minus x squared, his antiderivative is not an elementary function. It's what we call a special function, which is the sort of bigger class. Yeah? Special function. Okay, now, and there are lots of different special functions, and they're really interesting. You can do all kinds of interesting things with them. Now, this begs the question, why would Dr. McKinney care about the integral of e to the minus x squared, right? It looks like it's just something I pulled out of a hat to show you, nope, not everything is elementary. You can't actually find an antiderivative of this thing. Get over it, right? The reason I picked this particular one is that the e to the minus x squared is basically the bell curve, okay? So if let me flop over to Mathematica here for a moment. Right, this curve here, this is basically the bell curve from probability theory. And I say basically because I would have to like scale this thing a little bit to make it like have total area 1. That makes sense, right, for 100% probability. The mean is in this case 0. You give me a standard deviation, I could cook it up so that the curve has that standard deviation. So there, if there's a 1 over square root of 2 pi and some other garbage, but point being, like, it's basically that curve with where I've swept some details under the rug. So being able to integrate this thing is equivalent actually to answering questions in probability, but I can't integrate that thing. So, as Shakespeare would say, there's the rub. We can get close, and that's what we're going to do, right? So it seems like a broken word from our conversation earlier this morning. So in my computer science class that's right before this class, we were discussing how accurate or inaccurate can you approximate pi well, in different computer arithmetic schemes. So, how many digits do you get, and how many digits do you need? Yeah, I mean, it assumes obviously estimates for the diameter of the known universe and that it's circular, but uh, some of those things are sort of open questions in cosmology. But um, and of course, the key there is the word observable universe because you know, well, we don't know, right? There's no way to tell. The universe is, you know, say 15 billion years old roughly, and uh, so anything that's more than 15 billion light years away, we would never be able to see, right? Now that's not entirely accurate because the fabric of the universe itself has been expanding, and so what? Yeah, it's complicated. So anyway, take a physics class or 10. Um, yeah. Okay. So anyway, so what we want to do is be able to find integrals of definite integrals of things where it's either impractical or flat out impossible to actually get an antiderivative. Okay. And so what we'll do instead is sort of settle for, well, we can't get it perfect, so let's just get it as close as somebody might demand. Okay. So can we compute this numerically, get a pretty good answer, and be content that that answer is pretty good? That's sort of the goal. Okay. Okay, so let me switch back over to the sheet, and I need to set up a thing for my button on this dude. Okay, so there's 5 methods that we're going to use, 2 of which, or possibly 4 of which, you may have seen before. We can use rectangles in 3 different ways. So this is the so-called left, right, and midpoint rules. We could use trapezoids, or we could get really fancy and use parabolas, and that's called Simpsons rules. So we'll talk about him at the end. Okay, so on your sheet there, the little grid lines didn't print very well, but this is how they were supposed to look, is that at 0.5, 1, 1.5, 2, and 0, I drew grid lines. Okay, and so if I wanted to approximate the area that's underneath that blue curve, okay, that's e to the minus x squared, um, I could inscribe a bunch of tiny little rectangles, add up the total area of all those rectangles, and get something. Okay, good.
It looks to me like those. So from when x equals like 0.85 or something like that,
Mm-hmm.
from that point it looks like it's symmetrical. So why couldn't you just take like a big rectangle and then like
Half it. It's not quite.
So it's not. It's not.
Yeah. So, I mean, you could, and that does give you an approximation. It's just not going to be as good as if you use multiple rectangles. Okay. And we'll, because that's actually doing a trapezoid rule, but with just with one trapezoid, because we can kind of think of a triangle as being a degenerate trapezoid in a sense. Okay, so if I do this with left-handed rectangles, what the left versus the right hand means is, well, first off, if I'm going to use 4 rectangles, how wide is each one going to be? And I'm doing this on the interval from 0 to 2. Half unit, okay? Do we have to make all the rectangles the same width? We don't have to, but it's way more convenient if you do so, okay? Because it'll simplify some arithmetic later. So let's just decree that we will always use the same width for each rectangle, whatever that is. Okay, so how did I get 0.5 units? Well, how wide is my entire interval from here to here? 2 units. And I chose to divide it into 4 rectangles. And the last time I checked, 2 divided by 4 was 1/2. Okay, if I wanted to use 10,000 rectangles, obviously they'd be a lot tinier, and it would be 2 over 10,000. would be the width. Okay, so you compute the width based on how many things you want, and for the sake of demonstration, I've kind of cooked this in advance to make the arithmetic easy, or as easy as possible. Okay. Okay. So what's the formula that I'm going to need to write for this? So sorry, what makes a left-hand rectangle a left-hand rectangle? Well, so where my cursor is on the screen, a rectangle that is 0.5 units wide, I have to decide, is its top left corner going to intersect the curve, or is its top right corner going to intersect the curve? If I choose the top left, that makes them left-hand rectangles. And if I choose the right, then, well, that's the right. Okay, so what are the left-handed rectangles going to look like here? The first one would be, what would its height be? It'd be 1 all the way up at the top. So what would the area of that thing be? It'd be 0.5, right? Because its width is 0.5 and its height is 1. Okay, what about the next one? Well, its height would be, well, it looks like it's just shy of 0.8, right? So 0.7 something or other. So it would go over here and then down. And then we would just keep doing this until we're done. Okay, does that, at least in theory, make sense? Okay, so let me actually see if I can do this. I'm not sure if this is going to work. There we go. What do you mean? I'm sorry.
Well, I didn't know the difference. I looked up, so left hand is where like the left part of the rectangle touches, and then right is where the right touches. So like, how do you choose which one?
Oh, okay, good question. So you actually, for the sake of demonstration, will just do both, right? So there is no choice. Just do both of them
Oh,
because I said so. All right, so yes, so we could choose left, we could choose right. Now, Cole's question is, why should you choose one versus the other? Well, actually, this example will illustrate uh, some reasoning by which to make that determination. Okay, so if I do left-handed rectangles on this, then first off, let me define my function. And then the second would be, the left-handed rectangle would be 0.5 times f of 0 plus 0.5 times f of 0.5 plus 0.5 times f of 1 plus 0.5 times f of 1.5. Okay, so how did I get, so this would be the left-hand area. How did I get that formula? Okay, so what did I do there? Yes?
your rectangles have the same width,
Mm-hmm.
so it's the width times like the point. So you're going like each half point. So
Yeah,
the left,
exactly.
the left started.
I'm just doing width times height, right? And I chose in advance that all of these would have 0.5 as their width, okay? And then what are the heights? Well, those are given by the function. So I plug in 0, 0.5, 1, or 1.5 to the function to get the height of each of the 4 rectangles. Okay,
In theory, you add the 0.5, 1.52.
and that's the right-hand rule.
Oh,
Yes. Okay. So if so, look at the graph here. Um, well, here, let me redo the graph. Let me just do this from say 0 to 2, since that's what we care about. And then let me put the grid lines in. Okay. Um, so got my grid lines, right? This is, you're basically looking at how I made the sausage, so to speak. Um, so yeah, so how many points are there from 0 to 2 with 0.5? There are 5 points. How many do I need to do one of these rules? I need 4 of them, right? So the difference between the left and the right-hand rule is just which points you leave off. The left-hand rule, you use the first 4. and leave off the last one. And the right-hand rule, you omit the first one and use the last four. Okay? So there's that. The other thing that I want us to notice here is the way I typed my formula. Is that the best way to write it? Why not? Exactly. So I can actually, how many arithmetic operations would we have to use or perform to compute it as I've written it? We'd have to do 4 multiplications, 4 function evaluations, and 3 additions. Okay? Right? As I've written it. But I could also write it like this. Okay, which one's more efficient? The latter one is better because it only has 1 multiplication, 3 additions, and 4 function evaluations. Okay, and we could get away with that. That trick worked because we said the widths would always be the same, which means we can factor that out. Okay, now this may not seem like a huge deal when we're just doing this with 4 points, but if I were programming a computer to do this, the difference between doing 100,000 operations and 50,000 operations is a pretty big difference, right? So I'd much rather do 50,000 if I could get away with it. Okay, so that's the left-hand rule. And what's the only thing that would change to make this the right-hand rule? Yeah, exactly. Just offset it. So right-hand rule would be basically that. Okay. So all I would do is leave off the first one, but otherwise everything looks pretty much the same. Now let's compute both of these things and see what we get. I forgot to define the function. There we go. Okay, so Mathematica dutifully crunches the numbers, and we get our left-hand approximation is 1.1, our right-hand approximation is 0.63. Those are relatively far apart, aren't they not? Yeah. Okay, we could take the average, right? So to split the difference. We'll talk about that in just a second. So looking at the graph, just kind of eyeball it. What do you think that the answer is? Like, what do you think, roughly speaking, the correct answer is, or close to it? 1? That seems pretty reasonable. Okay, so how did Cole get 1? Well, if I think of what's the area of the entire square or rectangle that's in view, it's 2 units, right? I've got height 1, base 2. And this curve kind of splits it roughly in half, so maybe 0.5-ish, or sorry, 1-ish. Well, yeah, I mean, so how could we get this approximation more accurate? Well, we could do this rectangle business, but what about if I use 10,000 of them instead of just 4? Yeah, the more rectangles you add, the more precision you get, but the more work you have to do. So take your pick. You want to do, are you lazy or are you precise? Right? If you're both, you have a bad day because you, like in numeric approximation, you have to choose where you are on the lazy to perfect continuum, right? If you want to be more lazy, then you're going to be less precise. Sorry. So that's just them's the breaks. Okay, so is the left and right hand rules, do those make sense now? Kind of just, it's just number crunching at this point. So what was Cole's observation? Well, the left hand rule and the right-hand rule, we're pretty far off. Okay, in particular, look at your sketch. The left-hand rule is a gross overestimate, right? And how do you know that? Well, because each rectangle overshoots the function. Yeah? And what about the right-hand rule in this case? It's a gross underestimate. Its rectangles all are under the curve. Okay, so this porridge was too hot. That porridge was too cold. But perhaps another bowl of porridge is just right. Okay, exactly. So I could say, what about if I average those two answers? All right, so this would be to compute, I'd get this, which from our eyeballing it seems better. Okay, and averaging it is called the trapezoid rule. Okay, so let's sort of think about why that's called the trapezoid rule. So actually, you know what? I'm going to pop open here a handy dandy program so I can draw pictures. All right, so hang it, if I can type today. All right, so sorry, the Zoom is being okay. So here's my curve, right? And why we're going to call this the trapezoid rule, let me zoom in just a little bit more. Okay, is so first off, let me draw a left-handed rectangle. Okay, and let me say E equals 0.51 and F equals 0, F of 0.5. Oops. Hang on one second. Okay. Because what I want to do is draw an actual rectangle. So this, okay, would be the rectangle if I did a left-handed version. Okay. And this, that's sort of slightly darker in color, would be a right-handed rectangle. Okay, and if I average those two areas, then what I'm actually computing is the area of the trapezoid ABCD. Okay, so if I connect those 2 points with a slopey line, right, the average of the two rectangles area is the area of that trapezoid. Okay, do you guys buy that? Okay, because the area formula for the trapezoid is it's the base times the average of the heights. Okay, and so that's equivalent to just averaging the two rectangles area. Okay, so does the trapezoid, it does better than either of the two rectangles individually, right? For the particular trapezoid I've drawn here, is this an overestimate or an underestimate? It's a slight underestimate. Okay, it's underestimate because that line is below the curve, and it's slight because, well, that looks like it's a relatively small error that we've got there. Okay, now that is just one of the four trapezoids that we would draw, But do you guys buy that the rest of them are going to look basically like that? Just shift it over a little bit. Where would the overestimate trapezoid be? Bingo. Okay. So notice that this function is on the interval that we care about it. It's decreasing. Okay. But what's going on with the concavity? What's the concavity of the function up to, oh, I don't know, maybe roughly x equals 1? It's concave down, right? And so notice how when the curve is concave down, our trapezoid is underestimating. Over there close to 2, so if I drew this for 1.5 up to 2, what's the curve look like there? It is concave up, okay? And so the trapezoid would actually slightly overestimate. Okay, so if one rectangle slightly underestimates and another rectangle slightly overestimates, it's not really obvious whether or not this one's going to over or underestimate, right? It depends on, well, the relative sizes, okay? So if the function has so like if we just were saying to use uh, one trapezoid on the interval from 0 to 0.5, then we could answer that question no problem. That definitely underestimates. Okay, but it's going to depend on the concavity and whether or not the function's increasing or decreasing. Okay, and those, keep in mind that idea of that the second or first or whatever derivative is going to be important, because that's what we'll use on Wednesday to analyze this stuff even further. So essentially today what we're doing is how do the rules work? I'm going to post a video for how do you make Mathematica do this. And then Wednesday we're going to talk about can we analyze the error and give estimates for how good the answer is going to be without actually having to compute it. Okay, so could we understand sort of the limits of computation? That's the Wednesday. Okay, so that's the trapezoid rule. Does that make sense? All right, now, on the other hand, I could have averaged in a different way, which is to say, so let me go from, let me throw some extra points on here. Okay, so for the next rectangle, this would be averaging a different kind of way. So I could say, all right, I used left-handed rectangles or right-handed rectangles. What about if I split the difference and made the height depend on the middle of the rectangle, not the left or the right-hand edge? Okay, so that would be like, for example, this guy. He's not a left-hand rectangle. That would be have its top left corner at the point D. He's not a right-handed rectangle. That would have the top right corner at the point H. He's somewhere in between, okay, where the height is given by the middle of the interval, not the left or the right-hand edge. You don't like that? Why not?
But it works. It's just but like your next rectangle.
The formula is a bit messier, okay, is
Yeah.
the problem with this one. Okay, but in theory, would that not also be a way of sort of splitting the difference, right? Now, you might ask, how is this actually different than the trapezoid rule? Like, is this genuinely a new rule? And the answer is yes, okay? And here's why. Here, I'm averaging the two endpoints before I plug them into the function. And with the the trapezoid rule, I'm computing the answers and averaging them after I've computed them. Well, functions are not all linear, right? So these two methods would be identical if the function were linear, but that's boring, right? We shouldn't need to do any of this fancy schmancy rigmarole if we're integrating a linear function. Okay, yeah.
Is it possible to take the double derivative of interval 0 to 3 of this one, or this function?
So to say that again, to do what now?
Is it possible to take like a linear line to average the slope from 0 to 3?
Oh, to come up with the average value of the slope?
Yeah,
Uh,
like a derivative somewhat.
yeah, but then you would turn around and integrate that because average value means to do an integral.
So if you found that value and then got the area, is that a different way of approximating?
Sure, it'd give you an approximation. Question is, how good is it?
So it's probably less accurate.
It depends, right? Depends on the properties of the function. And yeah, I mean, the advantage to that is that it's less arithmetic,
Right.
right? You're using your brain instead of doing brute number crunching. Sometimes brute number crunching is called for. Okay, so if we average the x coordinates before performing a function evaluation, that gets us the midpoint rule. If we do the averaging after we've computed everything, that gives us the trapezoid rule. Okay, and as we're going to see, the two have similar levels of accuracy. Here, what's nice about this midpoint rectangle is notice that this little chunk above is roughly speaking the same looking as that little chunk below. Now, I say roughly speaking because they're not identical, right? Which one do you think is slightly bigger? The above part or the below part?
What do you mean bigger?
Well, so like they almost look like triangles, okay?
So the area?
Yeah, so which one do you think is
So it's actually the top one because it's like it technically has a little outlet.
because of the concavity? Exactly. Yeah. So the top one is a little bit too big. It is it is bigger by a tiny amount compared to the one that's from point I to point H, because the curve is still concave down there. If it were the other concavity, it'd be the other way, right? Okay, but it looks pretty close, right? Yeah. Okay. Roughly. All right. So let me go back to here and here. Okay. So let's go over to this other sheet. Here's the sigma notation formulas for the midpoint rule and the trapezoid rule. Okay, so notice what's happening with the midpoint rule. And I just realized there's an error there. This formula right there is wrong. I'll fix that. It should be um, a formula for an odd number, because if I think back to the picture, if I use the midpoints, what am I going to plug in? I'm going to plug in 0.25, 0.75, 1.25, and so I want to think about that as of delta x over 2, but I want only the odd multiples. So I need to do, I think, a 2k minus 1 thing. Okay, I'll fix that and then re-upload the document. Um, yeah, okay. Um, so this right here, this formula for k, it should actually be 2k minus 1 in parentheses. Okay, and think about that for a second. What is 2k minus 1 always going to produce for if k is a whole number? If you double a whole number, what kind of number do you have? An even number. If you take one away from an even number, what do you always have? An odd number. Okay, so 2k minus 1 will give me the formula 1, 3, 5, 7, and so on, and that's the way I want to count for that rule. Okay, so I'll fix that. The second thing here is the trapezoid rule. As nasty as that looks, what really is it doing? What's the area of a trapezoid? The base times the average of the two heights. Yeah? Okay, so what's one height? It's f of something. What's the other height? It's f of the next something. And then I divide by 2 to average them.
Same value then.
What do you?
Why is A the same? Like, why is it 2 A's?
Because A is the far left endpoint. So like A is 0 in the example that we're using. Because notice that A is like what I want to approximate the integral from A to B, right? So in our example, A is 0 and B is 2. What makes it not the same, though, is the K delta X part. Okay. Now, sigma notation, do you guys remember this from high school? No? The big letter sigma?
Oh, yeah.
You
Well,
remember the letter, but not.
sum of all, like, something.
Yeah, that's all that the thing means, is I'm going to add up a bunch of stuff, right? I'm going to add up things on the right where the counting variable starts at 0, 1, whatever, and goes up to something else. Okay. Now, in computer programming, this should be the idea of a for loop. Okay. And in fact, the video that I'm going to post on how to make Mathematica do this, you could actually type in the sigma notation into Mathematica and it'll do it, right? Which is fine. But I'll show you guys another way to do it, sort of a more of a computer programming style, using a loop, just for your own edification. Okay, good. All right, let's talk about Simpsons rule, because this is, I think, the most exciting one. So let me take my curve here, and actually, you know what? Let me open up. Let me save this. Actually, not. Hold on. I think. Oh, wrong directory. Okay, so I want Dropbox, Monash, teaching. Oh no, wait, it's Dropbox apps. I want Math112, worksheet chapter 5. Okay, so what I've done here is something that may seem, why on earth, seem funny. Why would I ever do this to myself? So what I've got is in red, or sorry, in blue, I have the e to the minus x squared curve that we've been considering. And I have 5 points on that curve, A, B, C, D, and E. Okay, good. So we used the points A, B, C, D, and E in 3 of the methods, 3 of the 4 methods that we've looked at so far, the left and right hand rules and the trapezoid rule. Okay, and the trapezoid or the left and the right hand rules are basically doing linear approximations to fit to that curve, right? The left and the right hand ones used horizontal linear pieces. The trapezoid rule used a connected line. So that's what we call a linear interpolation. Okay. Well, who says that I can only use lines in this class? Okay, a linear interpolation is good. Can we do better? Okay, what would be one step up, excuse me, from linear? Quadratic. Okay, and so Simpson's rule is doing what we call quadratic interpolation. I'm going to approximate the curve by approximating it with a bunch of parabolic little pieces. Okay, so the points A, B, and C uniquely determine a parabola. Right? How many points do you need to find a conic section? How many points are sufficient to define one? Do you guys happen to remember from high school? It's 5. 5. But if I also tell you what kind of conic it is, you can reduce the number. Okay. So if I give you 5 points, that is unique. That is enough for you to figure out a single conic section that goes through all of them. If I tell you here's 3 points and I want it to be a parabola, that's also sufficient. Okay. So the point A, B, and C uniquely determine a parabola, and the first one there I've graphed in red. Okay. The points C, D, and E uniquely determine another parabola, and that one I've graphed in green. Okay. And you'll notice between the points C, D, and E, can you tell the difference between the blue curve and the green parabola? Barely. They are really, really close together. Yeah? Okay. So if I want to find the area underneath the blue curve from, say, the part of it we're running from the point C over to point E, could I instead find the area under the green parabola? Yeah, and the reason that that's good is because it's pretty easy to find the area under a parabola, right? We can do calculus. That's not rocket science. Well, we can do rocket science also, but right? Because what's the integral of a quadratic going to look like? It's going to be something cubic, right? And we can plug stuff into that. Okay. Now we could do the same thing over there with the red parabola. Okay. So here's where Simpson's rule gets a little funny. What was the number of rectangles that I was using in my rectangle scheme? 4. And I just picked that for sake of example. I could have used 10,000 if I had wanted. Okay. So anyway, we chose 4. The Simpsons rule requires that that number be even. Okay, there was nothing about the left-handed or right-handed rules that required I used an even number of rectangles. I could have used any number, and I just picked 4 for sake of demonstration. Okay, good? No, for Simpsons rule, the number n has to be even. Now, there are no rectangles there, right? Because I'm talking parabolas now. Yeah. Okay, so the number of points n must be an even number. And the reason is because how many parabolas do I have up there? It's actually 2, because one of them is the original curve, which is not a parabola. Okay, so I've got the red one and the green one, right? So if I do the rectangle method with 4, I draw 4 rectangles. So that the equivalent Simpsons rule scheme would be to still have n equals 4, but to find half of that number of parabolas. And that's why it's got to be an even number, because if I have 5 and I try and half that, what does it mean to have 2.5 parabolas? That doesn't make sense. Okay, so it's always got to be an even number.
So when you're talking about points,
Mhm.
5 points.
Okay, yes, there are 5 points. This is like that Star Trek episode. How many lights do you see? There are 5 lights. No? Okay, never mind. So there are, yeah, that's maybe a good observation. So how many points really am I using here? 5. Okay, but in terms of the rectangle scheme, how many would I really be using? Just 4. Okay, and with left versus right-handed rectangles, the difference is which 4 are you using? The first 4 or the last 4? Yeah. Okay. So maybe think of it that way, is that I'm thinking of for widths, not for points. Okay. This is a fence post problem, right? So if you've got 10 feet of fence and a post every foot, how many posts are there? 11, because there's one at the far end. Otherwise, your fence is going to fall down, right? Well, maybe not, but okay. So yeah, the counting here is kind of annoying. If there's any one thing you should learn about mathematics, is that counting is hard. Okay. All right. So what you're doing with Simpson's rule is looking at basically what are these parabolas, and really, I don't care about the parabola itself. I care about the area under it. And it turns out that it's a lot easier to talk about the area under it than actually to come up with the formula. And I'll just put this up here, and this is sort of where we'll quit today, is it turns out to be this for our example. Okay, it's a really nice pattern. Ones, fours, twos, and then if you've got more points, the fours and the twos will sort of alternate. Um, but yeah, it turns out that it's really easy to compute the area under that thing. And if you want to see a derivation of it, of why that is what it is, many years ago I wrote some notes. You can get these off of my Dropbox website. And what I did was I derived Simpson's rule using a theorem from Archimedes. So this is probably what Simpson was thinking himself when he came up with this. Although, let me go back to the other page here. So that's linked on there. Um, there is actually a Kepler supposedly also solved this problem, and the problem he was interested in was approximating the volume of a wine barrel, right? So if wine barrels aren't a standardized size, which they weren't back then, how could you determine how much wine is in the barrel and therefore how much you should pay for it? Um, so, yeah, anyway. All right, well, so I will post a correction to the sheet and the crash course in doing this in Mathematica video. And then on Wednesday, what we're going to look at is to say, all right, we know that these schemes are not perfect. There will be error. Can we quantify how good or bad our computations are? And if I tell you, I want you to get me an answer that's within 1/10,000th of the correct answer, how many rectangles or whatever do you need to use? Okay. All right. So we will see you guys later.